Hello and welcome you all to the 6th lecture on electroweak interactions in the standard model of particle physics. And in the first few lectures, basically we talked about special theory of relativity, Lorentz transformation, and we also talked about the cross sections and decay weights, the phase space which is Lorentz invariant and so on. And in that component we basically elaborated upon the phase space part mostly, leaving aside one of the important ingredients which is called the transition matrix element square, and that part we said that this requires basically the underlying theory which will govern the kind of interactions from state I to state F. Now that is what we are going to do, or rather we are starting the process of building a consistent theory which can describe these interactions between the fundamental particles. So this is the first lecture of doing that, in which we try to address what we called relativistic quantum mechanics. Okay. So let us get started. So this is what I already said, that in the transition probability that we actually constructed from one state to the other, more specifically in the decay width or in the cross section expression, you remember we had essentially three things. One essentially is the phase space, which comes from the kinematics of the process, like how many final state particles are there, how many initial state particles are there, like as I say whether a decay is a 2-body decay or a 3-body decay, etc., and that is what is kept in in a Lorentz invariant way. That was written in a Lorentz invariant way, and that is what is called the Lorentz invariant phase space. However, the fundamental nature of the interaction, that is which kind of process which governs it, it is actually embedded in the matrix element squared of the process, which is like a mod of MFI square, which was there in these expressions. And this gives you what is called the dynamic of the process. For example, if you look into the electron muon scattering to produce electron muon, or you think of E plus E minus annihilation to produce a muon and anti-muon pair, these are two different processes with different cross sections. However, the phase spaces are essentially the same for both the processes, because both have two initial state particles, two final state particles. So the phase space of both these processes are identical, whereas the flux factor is also the identical, but the differential cross section, or rather the difference between these two processes, will come from the matrix element squared. Okay. So in order to construct this matrix element squared, we need a consistent theory. Now what kind of theory that we are looking forward to build up? So you remembered in the first class we talked about that when we are trying to describe the fundamental particles, we have to adhere to the feature of quantum mechanics. At the same time, because these are very fast moving objects, we need to abide by the special relativity, or so to say we have to make them Lorentz invariant. So therefore we need to have this marriage of quantum mechanics and relativity, that is what we call the relativistic quantum mechanics. But by the end of the class, we will actually see that having a relativistic quantum mechanics, the way that we actually talked about the non-relativistic case, is not possible, and that gives rise to the construction of what we call the quantum field theory. Okay, so let us get started and let us try to see. First, you remember that in the non-relativistic case, how the energy and momentum are related. The relation is simply E is equal to p square by 2m when there is no potential energy. Now we said that if we have to do a quantum equivalent of this equation, then we have to convert everything into an operator, and this is what we have learned, that E is an operator which looks like IH cross del del t, whereas the momenta is something like minus I H cross gradient. Okay. So these are the operators that we came across when we constructed our quantum mechanics. So every observable or observation is an act of an operator acting on a wave function space, giving you some answers or a result of that operation. So if we have to now convert this E is equal to p square by 2m, this equation quantum mechanically, and using these operators, we can simply say that this is IH cross del phi del t, where phi is what is called the wave function on which these operators are acting, and on the right hand sides we will have minus h cross square by 2 m del square phi, correct. So, phi is a function of position and coordinates as well as time, right. And I do not have to tell you that this equation is one of the most familiar equation that all we are accustomed to, and this is what is called the Schrodinger equation, right. This is the famous Schrodinger equation, and we have all learned how to solve this equation, and primarily this is because it is a free equation. The solution can be written in terms of n into e to the power minus I omega t minus k x, that is like a plane wave solution, or in the 4 vector notation we can simply say that this is n into e to the power minus I p dot x, where p is the 4 momentum here and this x is nothing but the 4 position, whatever way that you want to say. Okay. So, this is describing basically an incoming wave and which solves the Schrodinger equation. So, for example, if you take the momentum operator on this phi, what you are going to get is minus IH cross del acting on this will give you H cross k phi x t. On the other hand, if you operate the energy operator on this phi, what you are going to get is H cross omega phi x t. So, basically you can see that you are actually getting a positive H cross k, you can think of a positive momentum, and you also have the positive energy which is given by H cross omega. So, this is basically describing the case of a wave with positive energy and positive momentum, right. So, this is how the equation is constructed for the non-relativistic quantum mechanics and what is the interpretation of its solution. Now, let us try to think of what we can do non-relativistically or rather relativistically. So, relativistically the energy momentum relations are different, and you can tell me what is the relation. So, it is basically E square equal to P square C square plus m square C to the power 4. So, therefore, if I have to write the E, this has to be written as E is equal to P square C square plus m square C to the power 4 whole to the power half. Once again, if you convert them in terms of energy operator, that will be E I h cross del del t, and P operator will be minus I h cross del, and so therefore, this expression relativistic energy momentum relation, if we have to have a quantum analog of this equation, that will turn into something like I h cross del phi del t is equal to minus h cross square del square, right, del square plus, and let us add those c squares also just to make sure that we have everything on board, then plus m square c to the power 4 phi x t, right. So, however, if you look closely into this equation, because now when we are actually doing it relativistically, we need to construct the equations in a way which involves Lorentz covariant objects, right. So, that is what precisely we talked about, but this equation somehow does not look like one which can be converted in terms of 4 vectors or the scalar product of the 4 vectors or something like that. So, I need to be able to see it in that way, so that we can say that this is Lorentz invariant. This equation does not actually change the form when you are transforming from one coordinate system to the other. So, does not look like covariant, and also we do not know how to find the square root of this differential operator. So, this is looking a bit awkward, right. So, therefore, instead of taking this E equal to P square C square plus m square C to the power 4 half, let us rather take the square form of this equation, which is E square equal to P square C square plus m square C to the power 4, And if I now want to write this equation in this form, then you will say this is nothing but minus h cross square del 2 phi del t square, and in the bracket this will be minus h square c square del square plus m square c to the power 4 phi x t, and this equation is what is known as the relativistic analog of quantum equation, the first one that we talked about, and this is what is referred as Klein-Gordon equation, or usually we say this is the KG. So, this is called the Klein-Gordon equation. Now, if you put h cross equal to c equal to 1, what happens? This equation simplifies and you have del 2 phi del t squared is equal to minus del square plus m square phi x t. Now, what I am going to do, that I am going to bring this del 2 phi del t 2 on the other side, and then what happens, that this equation is like del 2 phi del t squared minus del square phi plus m square phi is equal to 0, right. And do you remember what this object is? This del 2 del t 2 minus del square is nothing but the del mu or the del square, right. So, this is nothing but del square plus m square, and this del square is what we defined as del mu, the scalar product of the 4 derivative, where you remember that we had that definition of del mu, or rather the covariant component of that was defined as del t comma del. And so, then you know the contravariant one, because that will involve an operation with g mu nu, will have a minus del t comma minus of gradient, and so therefore, together del square del mu will become del 2 del t 2 minus del square. So, this is del 2 del t 2 minus del square. Now, this equation which we finally obtained here, which is like del square plus m square phi x equal to 0, where once again I have assimilated a 4 component notation. This x is x t comma x or x vector comma t or something. On the other hand, this part, the differential operator part, that is also Lorentz invariant. So, this is nicely covariant, and so we have a equation which looks like a quantum equation, which is obeying the relativistic energy momentum relation, and at the same time it is looking like a Lorentz covariant one. Okay? And once again one can show that phi x t, if we take the similar solution, the plane wave solution that we actually wrote before, which is like n into e to the power minus I e t minus p dot x, or rather phi x t is n equal to e to the power minus p dot x in the 4 component notation, is a solution of this equation once more, where you have this relation that E square is equal to p square plus m square, or in other words you can say that the E has to be equal to square root of p square plus m square. So, the solution of this equation is basically telling you that I can have both positive and negative energy solution, because if this relation that I am obeying is E square equal to p square plus m square, then I essentially have both the roots possible, and that is giving me a positive energy and negative energy solution. Okay. So, that is one important point where we have a departure from what we did non-relativistically, that we have both positive and negative energy solutions of the Klein-Gordon equation. The second point is the following, is that now if you want to construct a continuity equation out of this Klein-Gordon equation, which is actually of the form of d rho dt plus divergence of j equal to 0, which can also be written in a Lorentz covariant way using the 4 derivatives. I can also say that this is nothing but del mu j mu equal to 0, where you know j mu has essentially 4 components. The first component is what I call the rho, and that can be shown to be I phi star del phi del t minus del phi star del p del t into phi. This is what I call the probability density associated with this equation, and then there is a probability current which I defined as J, and that is essentially minus I phi star gradient of phi minus phi gradient of phi star, and J is called the probability current density. Now, what you need to do, I am not going to derive this equation right here, but you need to do it as a homework exercise. Start from the Klein-Gordon equation and try to find out the continuity equation where you can find the expression of rho and j as expressed here. So, you can clearly see from the expressions of rho and j that rho is actually rho has this derivative with respect to t, del phi del t or del phi star del t, whereas it is a nice analog that in the j you essentially have a spatial derivative, like gradient of phi or gradient of phi star. So, this basically says that I can simply construct a 4 current with this probability density and probability current density. I can construct a 4 probability current density, let us say in that way, which is j mu x, which can be defined as I phi star del mu phi minus del mu phi star into phi, following what we had. And when mu is equal to 0, this is going to give you rho. When mu is equal to 1, 2 or 3, this is going to give you the j vector. Okay. So, this basically says that mu equal to 0 is going to give you rho, and mu 1, 2, 3, this is going to give you j. Okay. So, this is the equation that we have. So, this is the continuity equation, del mu j mu equal to 0. So, the Klein-Gordon equation leads to a continuity equation which says that conservation of a 4 current where the j mu has a form I phi star del mu phi minus del mu phi star phi. Okay. So, this is what we say. Now, suppose I am going to put the solution that phi x equal to n into e to the power minus I p dot x, or in the vector notation it is n into e to the power minus I p dot x minus e t. Okay. So, if I now put this expression back into the expression of rho, say for example, rho is what? I phi star del phi del t. So, this is phi star. If you have, this is the solution that you have taken, then phi star is n into e to the power I p dot x minus e t, and then what will be del phi del t? That will be giving you I e into n into e to the power minus I p dot x minus e t. Then what you have? Minus del phi star del t, minus del phi star del t is going to give you this expression minus I e n into e to the power I p dot x minus e t, right, and then into phi, which is n into e to the power minus I p dot x minus e t. Now, you observe that in both these expressions the exponential parts essentially gets cancelled, right, and what you remain with is essentially that this is 2 into mod n square into e. Okay. This is very interesting. So, what you are trying to say is that the J0, the 0th component of the 4 current, which is probability density, is turning out to be 2 into mod n square into e, or in general, which I am not calculated, but you should calculate it back home. That will be a homework exercise, that the 4 current will be then related to 2 into mod n square into p mu, the 4 vector, the 0th component of which is nothing but the energy. Okay. So, now this result is something very important. Since in this particular case we said that we cannot avoid the negative energy solutions, and what we have shown here that the conserved current that this equation actually indicate to So, whatever the probability density that we can actually construct out of this turns out to be proportional to the energy. Since this energy can be both positive or negative, we cannot interpret rho as the probability density, because probability density becoming negative is completely unphysical. There is nothing as negative probability, I cannot construct that. So, this whole interpretation in the quantum mechanics that we essentially identify with the statistical interpretation, what to say, is not becoming quite sensible in the construction of the relativistic quantum mechanics. Now, we are going to talk a little bit about the Feynman-Stuckelberg interpretation, that everybody was puzzled about what exactly these negative energy solutions may indicate. So, then proposed that there is a nice way out of tackling this, which is to say that this negative energy particles, so these negative energy particles that you actually have are equivalent to antiparticles moving backward in time. Now, what does it mean? In order to do that, let us consider the motion of a charged particle in an electromagnetic field. Now, how shall I write this equation? This is basically the equation which we all know, like m d2 x dt2 is equal to the force acting on the particle, and in this case, electromagnetic case, this is actually the Lorentz force, which is q into E plus V cross B. Now, what I did, that I wrote this equation in a 4 component notation with an f mu nu and with a dx nu d tau, and I said that this part, the right hand side of this equation, which is giving you the Lorentz force, can be written as q into f mu nu into dx nu d tau. Okay. Now, if you look into this equation, there is an interesting point which we borrow. Suppose if you want to make this tau going to minus tau, okay, changing the sign of tau to minus tau. If you do that, then the right hand side of this, the sign of the right hand side of this equation changes, right? This will have a negative sign. Whereas on the left hand side, because it involves double derivative, the sign does not change. So, therefore, you can say that there is an equivalence of either changing the sign of tau to minus tau. You can also do that without changing the sign of tau. You can simply change the sign of q, because there is a proportionality with this q, right. So, this is an interesting point, that there is an analog between changing the sign of tau or changing the time direction to that of changing the charge of the particle. Okay. So, you can say that a particle therefore moving backward in time is equal to oppositely charged particle moving forward in time. So, there is a nice equivalence. But reversing the time essentially will change the momenta, p will go to minus p, say for example. Now, if I want to construct the electromagnetic 4 current that we actually did have, in that context, how exactly does it matter? So, you say that okay, we actually constructed a 4 current which takes the form j mu equal to I phi star del mu phi minus del mu phi star phi, but suppose this field or this phi or this whatever the solution of the Klein-Gordon equation actually have an electromagnetic interaction, then we assume that this must be multiplied by its electromagnetic charge q. So, you can say that I can construct an electromagnetic analog current like J mu electromagnetism, that will be q into the J mu that we constructed, and it turns out that this J mu was nothing but 2 into mod n square into p mu. So, therefore, the J mu electromagnetic is plus q into 2 mod n square into p mu, which you can, if you inflate the p mu, then that is nothing but E comma p, right. So, this describes a positively charged incoming particle with positive energy. The energy is positive, momentum is positive, the charge is positive. So, this current basically describes a positively charged incoming particle with positive energy. Now, let us do one thing, that let us change the sign of this energy and let's make it minus E here. Okay? So, the J mu electromagnetic is suppose plus q 2 mod n square minus of E comma p. This basically means that you have a negative energy incoming particle with positive charge, correct? Now, what instead I can do, that I can take this minus sign out of here, put it rather on this charge q and make it minus q, and here in the 4 current I will have it E comma minus p. So, what happens? This little arrangement or rearrangement makes the previous expression saying that it is a positively energetic particle having negative charge and which is having opposite momenta, which is moving backward or going outward. If that was the case, which was incoming particle, this particle must be going outward, or rather we say that this is the antiparticle which is going outward. So, in a sense there is an analog of a positive negative energy particle with positive charge to be associated with a positive energy antiparticle with a negative charge, right. If that was the incoming, this will be outgoing. So, therefore, the turn we can turn this unphysical negative energy cases to physical positive energies with the assignment of what we call the antiparticle. So, treat it as an antiparticle by changing the electromagnetic charge and swapping the sign of the 3 momenta. So, therefore, which was incoming now becomes outgoing. There is another way that we can actually draw this analogy. Suppose it is possible to think of these possibilities for a quantum particle to be emitted and absorbed into a system. Let us actually try drawing that and see whether we can actually find some equivalence in this process. Suppose I have a system with energy E, Q is the charge of the system and Q is defining the vector, the motion or the momenta of the system. So, this was before. Now, suppose you want to absorb a particle which has an energy E, charge small e, and it has a momentum p. Okay. So, the system after absorbing this particle, what will be the energy? This energy will be E plus capital E. What will be the charge? This will be q plus E, and what will be the momentum? This will be simply q bar plus p bar after it absorbs. Now, let us consider another case where you have a system with the same configuration like energy E, the charge q and the velocity q vector, small q vector, and what is happening now that there is an emission of a particle with energy E, charge small e and a momentum vector p. So, what happens to that system after it actually emits a particle of this kind? Then you say that the energy of the system becomes E minus E, the charge becomes q minus E and the momentum becomes q minus p. Excellent. So, this defines the emission of a particle. Let us now consider the case of absorption of a particle which has negative energy. Suppose you have minus E energy and the charges and the momenta are remain the same. What happens when you absorb this particle? The energy of the system becomes epsilon minus E, right? Epsilon minus E, the charge becomes q plus E and the momentum becomes q plus p. Now, let us think of emission of an antiparticle. So, what was the interpretation of antiparticle? That we are going to keep the energy positive, flip the sign of the charge. So, that becomes minus E, say for example, and momentum is also flipped to minus p. So, let us think of the emission of whatever that you call particle or antiparticle with energy E, charge minus E and momentum minus p. So, what the system becomes after it emits such kind of an antiparticle? The energy becomes epsilon minus E, right? the electromagnetic charge becomes, because you are emitting a minus E charge particle. So, the charge becomes E plus q plus small e, and once again the momentum becomes q plus p. Now, you can see that the energy configuration of the system after emission of an antiparticle of this kind of credentials is essentially equivalent to absorption of a particle with negative energy. So, therefore, you can say that this negative energy solutions can be treated as absorption of a negative energy particle is essentially the emission of an antiparticle with positive energy, but I am going to flip the sign, electromagnetic charge. So, therefore, in a sense finally what we can say that the solution of the Klein-Gordon equation, this now must inherit not only the incoming positive energy particle which is having of the form of e to the power minus I e t minus p dot x, but at the same time we must have outgoing positive energy antiparticles also, okay, and that will have an exponential like e to the power I e t minus p dot x, and phi should incorporate both this particle and antiparticle solution. So, this solution as you can see is not inherently a single particle description which you usually have. The wave function interpretation in quantum mechanics is usually to have to describe the single particle case. So, as we are forced to consider both particle and antiparticle, this phi x actually goes beyond the interpretation of the single particle quantum mechanics. So, this ensures the death of single particle quantum mechanics which we learned non-relativistically, and that seeds the requirement of constructing what we call the quantum field theory, but we have to embrace the many particle interpretation, while instead of then talking about this phi x to be a wave function, we are going to say that these are nothing but the fields which actually describes both the particles, rather incoming positive energy particles and outgoing positive energy antiparticles. So, therefore, the relativistic quantum mechanics is not really a relativistic quantum mechanics, but the consistent description can only be given in terms of quantum field theory. So, with this we end today, and we are going to take up something more interesting which is called the Dirac equation and its solutions in the next lecture. Thank you.